Alright, so we're going to continue and wrap up section 3.2. Based on everything that we have been working with, we're going to put all that information together, and the objective is to sketch a graph without a calculator. That's what sketch means. Sketch, don't use a calculator. We're going to sketch a graph based on all the information we've been working with in this section so far. So this is going to be our approach to sketch that graph. We're going to, 1, apply the leading coefficient test to determine if the graph rises or falls to the left or rises or falls to the right. We're going to find the real zeros, which are the x-intercepts, to plot those. And then we're going to plot a few additional points to kind of nail down the graph, and then we'll draw the graph. So we'll be looking at 2 examples. Our first example is the cubic function x cubed minus 9x. Alright, so applying these 4 steps here, the first step is to apply the leading coefficient test. So the leading term is x cubed, that's the term with the highest exponent, or n value. And because n is odd, and a sub n, or the coefficient, is positive, we can look back at our notes and describe the n behavior. So for step 1, apply the leading coefficient test. Let's just organize our work in this fashion. Okay, I know that the graph is going to fall to the left and rise to the right. So that kind of gives us a visual that the graph comes on the screen from the bottom left and leaves the screen on the top right. Okay, let's find the real zeros. Replace y with 0. I'll trade sides. I see a common factor of x. I could factor this binomial if I wanted to, or I could just extract the roots, but I'll go ahead and factor it so we can kind of look at the multiplicity. Set each factor equal to 0. So these are our zeros, which again means these are our x-intercepts. So if x is 0, y is 0. Another point on the graph would be when x is 3, y is also 0. And when x is negative 3, y is 0. So we'll use those to help us in sketching the graph too. Okay? The third thing says plot a few additional points. Before I determine what points I want to plot additionally, I'm going to come over here and put in place what I know. I know I have 3 real zeros, 1 at the origin, 1 at negative 3, and 1 at 3. These are the only x-intercepts. The graph will never cut through this x-axis at any other place but beside these points. Alright, and using the leading coefficient test, the graph falls to the left, so it has to come up this way if it's falling from the left. Cuts through, crosses, since I have a multiplicity of 1 on each of these factors. So the graph will come up, cut through here, doesn't just touch it and bounce off of it. Cuts up, goes ahead, above. It's going to have to turn back around to come back and get this 0, fall below, and then leave because it rises to the right. So at least we know a general graph. But 3 says plot a few additional points. I might want to plot something that falls between 0 and negative 3 just to see about how high this graph might go. So I think negative 1 or even negative 2 would be a good additional point. I'm going to use negative 1, which means I'm going to go back to the original equation, and everywhere I see x, I'm going to replace it with negative 1. So the original equation was x cubed minus 9x. So negative 1 cubed minus 9 times negative 1. the result would be -1 plus 9. The sum is 8. So what that tells us is that this is the point -1, 8 that's on the graph. So at least we have an idea of how high. So if this is -1, depends upon how you want to scale it. It really doesn't matter. I'll say that's 8. So the graph has to at least go that high. It might go a little higher and then come back down. We don't really know. We don't really care. We're just sketching. So this graph's going to come something like this and back down. And remember, the graph was falling to the left, so we want to indicate that. I think another good point would be to do +1. So I'm going to come over here and evaluate the function at 1. So that's going to be 1 cubed minus 9 times 1. The result will be 1 minus 9. Doing those computations, I get -8. So another point would fall at 1, -8. So if this is +1, then -8 would be somewhere down here. And again, I don't know if it falls down below that or not, but we're just sketching. It has to turn back around, and the graph rises to the right. So we used the leading coefficient test. We found the zeros. We looked at the multiplicity. So the graph crosses through the x-axis because all zeros have a multiplicity of 1. We plotted some additional points. Using all that information, we got a pretty good sketch. Alright, for our second example, we have a 4th degree function with a negative coefficient. So that's like a parabola that opens down, because a parabola has an even exponent, so does this polynomial, but it has a negative coefficient, so it's going to fall to the left and it's going to fall to the right. Alright, step 1, the leading coefficient test. We just talked about it. Falls left, falls right. Basically, it means it opens down. Let's find the zeros. Okay, there's not a common factor to pull out, but that's okay. When this is an even exponent, or not even, doesn't have to be, but when this exponent is half of that one right there, we're going to be able to factor it into 2 binomials. I don't like the negative coefficient, so I'm going to multiply everything by -1. Changing all the signs. And of course it's irrelevant to multiply 0 by -1 because it's still going to be 0. If this exponent is half of this exponent right here, and this coefficient's 1, we can break it up into 2 binomials. This would have to be x squared to multiply by x squared to give us back to x to the 4th. What are factors of 20 that add to -9? Factors of 20 that add to -9 would be -4 and -5. Alright, I see that I can continue to factor this difference of 2 squares. So this binomial will break up into x minus 2 and x plus 2, both of which have a multiplicity of 1. Remember, the exponent is 1 here. So the graph's going to cut through the x-axis at these x-intercepts. I don't see that I can factor this, but that's not a big issue. We'll extract the square roots on that one, since 5 is not a perfect square. So set each factor equal to 0. So remember, this means that 2, 0 is an x-intercept with the multiplicity of 1. We have another x-intercept of -2, which again, remember, that means there's an ordered pair -2, 0 on the graph of this 4th degree function. And this one right here, since we can't factor it, that's okay. We'll just add a 5 to the other side, and we'll extract the roots. So we have positive and negative square root of 5. Both of a multiplicity of 1, since we didn't have an exponent of 2 or higher out here. Alright, and remembering that this means that we have another x-intercept of negative square root of 5, 0, and positive square root of 5, 0. Alright, looks like I'm a little bit out of room down here, so I'm going to come over here and do part 3, which is to plot some additional points. I'll leave some room for that. I'm going to put the graph over here. Before I plot some additional points, I might first put the x-intercepts on the x-axis and thinking about the end behavior from the leading coefficient test. So looks like I have 4 zeros. So negative 1, negative 2, there's negative 2, 0, positive 1, positive 2, here's a 0. Alright, negative square root of 5, well that's bigger than the negative square root of 4. Negative square root of 4 would be negative 2, so it looks like it's a little bit bigger. So it's going to fall somewhere right here, negative square root of 5. Likewise, positive square root of 5 would be bigger than 2, and it's going to fall somewhere about here. So we've got really close x-intercepts. It's going to be kind of tough for me to draw the graph, but we'll do the best we can. So remember, the graph falls left, falls right, so it's going to come up the screen here, hit this x-intercept, go through it, doesn't bounce off of it or touch it, and then come back down through here. It looks like the graph might come back up this way, and then back down through here and fall to the right. So I think the additional point here that I'm going to graph is just going to be 0. I'm only going to plot one additional point. I'm going to plug 0 into the original equation, which that makes it easy because when you plug 0 into negative x to the 4th, that zeroes out. This term will zero out. And we're left with negative 20. So f of 0 is going to equal negative 20. Which, remember, that means 0 is the x, negative 20 is the y. So that gives me an idea that the graph is going to touch at this y-intercept of 0, negative 20. Alright, let's put it all together. It falls left, falls right, so the graph's got to come up this way. Cut through that x-intercept, bounce back down here. It's going to come way down here, come back up through here, bounce down through here, and continue downward. If I wanted to find out how high the graph went in between these x-intercepts, I could choose a point somewhere in between here, but that's going to be kind of difficult, so we're not going to do that. We're just going to think that because these are close, it doesn't get very high. Alright, so we used the strategy of we applied the leading coefficient test to look at the end behavior. We looked at the zeros and we plotted some additional points to help us kind of nail down the graph a little bit better. Okay, so that's applying all our knowledge from the first part of this section.